Greetings everyone and Happy New Year. I hope you all had a wonderful holiday season and that you're excited to get back into another year. I'm sure I'm not the only one who missed our December math fix, so without further ado, let's get started.
Today's math fix is brought to you by F.BF.2, which asks students to write arithmetic and geometric sequences both recursively and with an explicit formula, use them to model situations, and translate between the two forms. Let's take a look at our problem today. Students are asked to help recent college graduate Joel figure out what starting salaries he should consider if he has a goal of earning a six-figure salary by the time he is 30. Where might students start with this? Let's jump in. Students might start by guessing and checking a starting salary and making some assumptions. They might assume that Joel is 22 years old now, just graduating from a four-year college. They might also assume that his salary is increasing by a standard 3% each year. He has 8 years then until he is 30. Guessing a starting salary of $50,000, students could multiply his salary by 1.03 every year to get the next year's salary until they get to 30. In this case, he would only earn about $63,000 by the time he is 30, so we need to try again. Students might have the misconception that since his salary increased by a total of approximately $13,000 over the 8 years when he started at $50,000, that they can then work backwards, subtract $13,000 from $100,000 to get approximately $87,000, and that will work. Let's see what happens. If Joel starts out earning $86,661, he will actually reach $100,000 by the time he is 27, again assuming the 3% salary increase each year. Students might wonder why this is the case. The answer lies in the fact that this is a geometric, not arithmetic sequence. Joel's salary is geometrically increasing each year, since to get Joel's salary from one year to the next, we multiply by the common quotient or ratio of 1.03. Unlike in an arithmetic sequence, where we are adding a common ratio each year, with a geometric sequence, the difference increases each year because we are taking a percentage of a bigger and bigger number, or in this case, salary. Given this information, we know that Joel can actually start looking for a job with a lower starting salary. Is there a way to work backwards from $100,000 to find the lowest salary he could find? Let's see. One way to go about doing this is to simply undo the process we've been doing. So instead of multiplying by 1.03 each time, we would divide by 1.03. In other words, to start, we want to know what value is $100,000 1.03% of in order to find the salary for the previous year. Doing this repeatedly would give a starting salary of approximately $79,000. Another way to do this, however, would be to connect to today's standard and describe that relationship recursively and explicitly. We can define the recursive formula as S sub n plus 1 equals 1.03 S sub n, where S is the salary, n is the number of years after Joel is 22. In this case, S sub 0 would be Joel's starting salary at age 22, which is unknown and what we are trying to determine. We can then define the formula explicitly as S sub n equals S sub 0 times the quantity 1.03 raised to the n power. Since we don't know S sub 0, and in fact this is what we are looking for, we can solve the equation for S sub 0, and then solve using S sub n equals $100,000 and n equals 8 since we want to end up with $100,000 after 8 years. This gives us a value of, again, approximately $79,000 that Joel would have to start by earning in order to end up making $100,000 after 8 years. Of course, we have made a couple of assumptions here, Joel's age and the percent salary increase he gets every year. Some extensions might be to ask students what would happen if Joel actually had gone on to graduate school and was starting off at an older age. What might his starting salary or percent increase need to be to meet the same goal? Or what if he receives bonuses or even commission for his work? These are all factors you might want to press students to explore.
And there you have it, folks, the January math fix. As you know, we love hearing about what you're up to in your classrooms all around the globe, so don't hesitate to share with us your take on this month's problem. Until February,